Welcome. This is a review of the third quarterly practice exam. Let's get right to it. Question number one is one of the limiting reactant. There are two questions involving limiting reactant. Make sure this works. Always keep looking up. Now this is blah, blah, blah. You don't have to worry about that. It doesn't affect your question. Notice you're given a balanced equation, which you're going to need. Before we do anything, before we can determine what the limiting reagent is, we're going to have to convert these masses to moles. So why don't we attend to that right now? Of course, we take the mass of N2 and its formula mass, 14 plus 14, the quotient, and we do the same for the 20 grams of hydrogen. Its formula mass is H2. When we solve, bang, we get 1.79 moles of N2 and 10.0 moles of H2. Of course, to figure out what the limiting reagent is, remember you have to divide both by their coefficients. The coefficient of N2 is 1, so that's 1.79. 10 moles divided by a coefficient of 3 is 3.33. This tells us, this is the smaller of the two number, that tells us that N2 is the limiting reagent. I want to warn you guys about something. Remember, when you use the number of moles, you use that as the number of moles of N2. That is the number of moles of H2. That is not the number of moles of H2. You use these. You do not use what you got after dividing by the coefficient. Part B, determine the number of moles of NH3 that could be produced. Well, your answer from part 1 is the limiting reagent. Remember, once you know the number of moles of limiting that you use, you can then use that to figure out how many moles of product, in this case, how many moles of NH3. Of course, you're going to have to look back at your balanced equation. I want to find out what is the ratio of N2 to NH3. I've got to go to my formula. I find that there are two NH3s for every one N2. So I'm merely doubling the number of moles of N2. And so I find out that I have 3.58 moles of NH3 that I could maximally produce from 1.79 moles of N2. Question 2, a very similar question. The same in that I need to determine the limiting reagent using, again, two given masses. There's some other things we have to do. Let's attend to that first. We need to, of course, convert those masses to moles. When I do the work, I find out that I have used 0.118, or I shouldn't say used. I have initially 0.118 moles of NH3, and oops, this should be O2. How many moles of O2, Mr. Zagelki? Well, I've calculated 0.078 moles of O2. Now, of course, that's not enough. Maybe it is. Probably not, to determine what the limiting reagent. Remember, I have to divide both of these by the coefficient. The coefficient in front of NH3 is 4. In front of O2 is 5. So the moles divided by a coefficient here is 0.03 roughly. Down here is 0.016. That's the smaller number. That means in this case, O2 is the limiting reagent. B asks for the number of moles of excess reactant that would react. Now, remember, we know how much excess we have. We have 1.118. We don't use all of it. I want to figure out how many moles of this I actually use. So, notice I have to base that on the amount of limiting that I use. So I need a conversion factor to take me from O2 to NH3. Go to the recipe, my friends. There are 5 O2s for every 4 NH3s. I have 4 NH3 up top. I have 5 O2 downstairs. Therefore, I find out that maximally, or the maximum NH3 that I'm going to use, is 0.062. Now, of course, at the very end of this, I want to find out how much I have remaining after using that particular amount of NH3. Well, remember up top, I know that originally I had 0.118 moles of the NH3. That was excess. I just figured out that I used 0.062 moles of NH3. The difference between the two of them is 0.0556 moles. That means there's still this number of moles of NH3 left after the reaction has finished. Number 3. 3 moles of an ideal gas. They give us the volume, 20 liters, a temperature of 293 K. They want to solve pressure. Therefore, the only one equation I could use to possibly solve this is PV equals nRT. The N is the number of moles of the gas. R is called the universal constant. That's given to you, 0.0821. The temperature in Kelvin, oh, they were so nice. They gave us Kelvin temperature. Can plug it up right in. The pressure is what I'm solving for, and they tell us we're in a 28-liter container. When I solve, my friends, I get a value of, 3.61 atmospheres. A very straightforward question indeed. Number 4 is closely related. Again, notice, what do they give us? They tell us about a gas, and we're looking for the volume, the V. We're given the temperature, T. We're given the pressure, P. Well, we have to use that formula. P times V equals nRT. You have to be careful about one thing, though. This formula deals with CO2, the pressure of CO2, the volume of CO2, the number of moles of CO2. Aha, be careful. They gave you the number of moles of HCl. I got to convert that to moles of CO2. What do? Well, I go to what I call my mole recipe up top. It says up top that for every 2 HCl's, I'm going to produce 1 CO2. So that's my conversion factor. There's 1 CO2 for every 2 HCl's. I solve for that, and I get 0.200 moles. Now I can plug everything into the formula. I plug everything in up top. I have 4 atmospheres of pressure. I'm solving for volume. I have that 0.2 moles of CO2, the universal gas constant, and that 300 degrees Kelvin. That gives me a final answer when I solve for X. X is 1.23 liters. Very good. Number 5 was that new topic we learned a couple weeks ago. It says calculate the ratio of the effusion rates of CO2 and SF6. You find on your reference table, you're given a formula for this. The ratio of the ratio of the rate of gas 1 to the rate of gas 2 is equal to the square root of the mass of the formula mass of gas 2 divided by the formula mass of gas 1. Well, let's call this gas 1, let's call this gas 2. So we're going to have the rate of CO2 relative to the rate as SF6 is equal to the square root of the molecular weight of SF6 divided by the molecular weight of CO2. Well, you have to plug in the gram formula masses of each one. Let's do that. That means the square root of 146.1, the formula mass of SF6, divided by 44, the gram formula mass of CO2. We get a final value of 1.8. That means that CO2, gas 1, travels 1.8 times faster than SF6. Number 6 and number 7 are essentially the same question. Number 6 is specific. It wants you to identify the I value of the Van Hoff factor for a compound. It could be 1, 2, 3, or 4, recall. Remember, if the value is 1, it's covalent, which means all nonmetals. It's a good simplification. 2, 3, and 4 are ionic compounds, 2 meaning 2 ions, 3 meaning 3 ions, and 4 meaning 4 ions that make up and break up, and into which they break up when the substance breaks down in water, called dissociation. Well, first off, A, B, and C are all ionic because metal, nonmetal, metal, nonmetal, metal, nonmetal. D is covalent. That's the easy one. If you're if you're covalent, that means your I value is 1. Ki breaks up into K and I, 2 ions. That means the I value is 2. CuSO4, be careful, breaks up into 2 ions likewise. A copper ion and a sulfate ion. You'll find sulfate on table E. That's 2 ions, so the I is 2. Na2C2O4 breaks up into 3 ions. An Na, another Na, and this C2O4 ion sadly to say, that's not on table E, but it has to be a polyatomic. 3 ions, I value of 3. Number 7 is the freezing point slash boiling point question. You're seeing it as the freezing point. There's one formula that you're always given, and there's another formula which you're not. The formula that you're given is the delta T formula. That means the change in temperature as a solution is formed, at which it boils or it freezes. This one answers the question posed. Freezing point is Kf, so you're given, notice, the constant for this particular solution, 1.86. We need the molality. Molality is like molarity. We're just going to give you the molality, 4.25. I value is CuNO3. That's ionic, so it's going to be 2, 3, or 4. Of course, CuNO3 breaks up into a Cu ion, an NO3 ion, and another NO3 ion. That's why it's an I value of 3. We do the math, and we find out that we get a change of 23.7 degrees Celsius. Now, friends, don't stop there. That's your change in the freezing point. But there's another formula you need to know, which is really a fact. We said that the freezing point of any solution is equal to the freezing point of its solvent minus the delta T from the formula, meaning the freezing point of any solution is lower by that amount than is its normal freezing point. Of course, you also need to come in knowing that the normal freezing point of water is 0 degrees Celsius, minus that 23.7 degrees Celsius, which gives you, of course, a negative 23.7 degrees Celsius. Now, of course, if we were dealing with the boiling point, it would be the boiling point of the solution equals the boiling point of the solvent plus the delta T. Now, in that case, the delta T, I should say the boiling point of the solvent, careful, you need to know that water boils at 100 degrees Celsius. So you would get the delta T from this formula, and you would plug in and you get a value above 100 degrees Celsius. So as I said, this you have to know. This you have to know. These you're given. This is for freezing point. This is for boiling point. Well, I hope that was helpful. And of course, good luck on the quarterly. See you in class.